So last week we stopped at the page, I guess page 15 about the introduction of the demand functions. And well, this actually comes from the part we have defined for the demand curve. Well, here you have to remember that in this class, we're going to introduce two terms, demand curve and supply curve, and find out the equilibrium part. The demand curve represents the function of the volume as the dependent variable, and independent variable is the price or the cost. While for the supply function, we will define the cost as a function of the demand or the volume. So those will be the difference. And because this would be two different functions to represent the relationship of the same two variables. So the equilibrium of these two functions will be the point we have to obtain for the transport system. But definitely that's the part we're going to try, the final conclusion we need to get for this class. So for the demand function, we can identify the two boundaries, two limited values. When the price is 0, what's the maximum flow we can observe, or when the price enters achieves certain value, the demand was too high for all the users, then the demand will be 0. So that will be the two boundaries of the demand function. And with that, you can find out connect the line from the any type of line from the original point P0 or from the two boundaries. The first one is P0, which would be the low boundary about the volume, to the highest boundary about the V0. And this line it could be any type of the functions for different type of the problems. And the line here is just one example. It's not an actual situation. But with this kind of lines, we will be able to find out the elasticities to represent the properties of the line. So the elasticity is defined as the changes in the volume with respect to the changes in the price. So you see what's the ratio of the changes in the price, say that 10%, and the elasticity will tell you what's the percentage of the changes in the volume. And we can, if the function is the continuous function, then we can derive that the elasticity equals to dV divided by dP times P divided by V. So that's the general definitions of the elasticity. Now let's go to see some specific examples. So the first thing is like first example is about the constant elasticity. So we assume that the elasticity is a constant value for all different P's or different V's. Say that the value is minus alpha. Then we can use this definition to find out what's the relationship between P and V. So with that, let's first go back to the definition. So the elasticity is dV over dP times P over V. So that's the definition about the elasticity. And now we can then use the knowledge of the calculus to quickly derive the solutions about the P and V. So if we do the integral on both sides, you can eventually find that the flow equals P to the power of minus alpha. So this is the function for the constant within a constant elasticity. And if we draw the figure, you can see this kind of decreasing curve for the price and the volume. And for this type of the curve, the elasticity is constant as minus alpha. And this indicates that the minus alpha shows what kind of percentages you can observe for the changes of the volume with respect to the changes of the price. So here, if alpha equal to 1, it indicates that if you have 10% increase in the price, then you will have the same amount of the decrease in the volume, because here alpha is or the elasticity is minus alpha, so it's -1. And that's for the case with alpha equal to 1. But for the second case, if alpha equal to 2, it indicates that if we have 10% increase in the price, you will observe twice of that amount for the decrease of the volume, which would be 20% of the decrease in the volume. So this is about the the second case, alpha equal to 2. Well, similarly, you can observe the get a similar statement about alpha equal to 3, equal to 4, and so on. So that's for the constant elasticity. And we can also go to check another function, the linear demand curve. So as we know the two limit values, P0 and V0, well, for the P and V space, the most straightforward connection for these 2 points is in a straight line. So which means that you can just you draw a straight line to connect P0 and V0. And well, with these 2 points, you can identify the linear demand curve. So in this case, P equal to P0 minus P0 divided by V0 times V. So when V0 is when V equal to 0, the value is a P0. When P equal to 0, it means you can find that V equal to V0. So this is a linear demand curve we defined. And now we can find out what's the elasticity for this kind of demand curve. So first of all, we need, from the definitions of the elasticity, we need to find out what's the value of the dP and what's the ratio of dP and dV. So for dP divided by dV, you can use in this equation to get the value. So the result is a minus V0 divided by P0. And for the elasticity, we need to time the ratio of P and V. So which will give you the final elasticity as V minus V0 divided by V. So this is the elasticity for the linear demand curve. And with that, you can see that if V equal to 0, which would be the first point, the point on the left, you can find out that the elasticity would be infinite. But if you go to check the point at V0, which means that P equal to 0, then you can get the value as epsilon equal to 0. So this is the elasticity at the right end of the demand curve. And that's the features about the elasticity of the linear demand curve. So we can see that for the high value of the price, the function is highly elastic. So for this part, it's very elastic. So if you have very small changes in the price, you will probably observe the very huge percentage changes in the volume. And well, if we go to the very small value of the price, so this region, then a smaller percentage change in the price will also result in the smaller changes in the volume. So that's the features from the linear demand curve. Of course, this will be two ideal case: the constant elasticity and the linear demand curves. This is not the common scenario applied for most of the real-world products. For the real-world products, instead of the decreasing curve or the linear curve, we will have the shape, the S shape, about the price and the volume. And when when the price is high, the elasticity is low. So the price decrease, the number of the trip increase, but it was slowly first, so it's not elastic. And also for the low value, you observe a similar thing. When the price increase, the number of the trip will decrease, but it's also slowly. So the demand curve is also inelastic for the high price and low price scenario, but only for the case when the price is in the middle of the range. You will observe that if you have a small change in the price, you will observe a large change in the volume or in the number of the trips. So this is quite common for most of the real-world products. For example, if we consider going to some theme park, and the P will be the price of the ticket, and V will represent how many people will go to the park. Well, first of all, if the price is very high, the say that $1,000, probably no people will go there. And even if you reduce the price from $1,000 to $500, still there might be a limited number of the people who like to go to the theme park. So that's the that's for the high price scenario. But for the another case, when the price is extremely low, say that if the price is only $5, and there will be a lot of people who would like to go to the theme park, say that there will be 1,000 people will be there every day. But if you reduce the price from $5 to say that's $2, that's a very huge reductions, very huge percentage of the reductions about the price. But still, you may observe that the increase about the volume, the people to go to the theme park, it might be still be around 1,000 or maybe a little bit higher, because the people who want to go to the theme park, they can go to the theme park at the price of the $5. Even you reduce the price to $2, it does not mean that there still have any potential people would like to go to the theme park, because most of them can afford it. But only when for the when the price is this is set as some intermediate range, say that it's $100, maybe there will be 500 people will be there. But if we reduce the price from $100 to $80, you may observe a huge amount of the huge percentage increase about the people to visit. So it might increase to 700, 800 people every day for the theme park. So this is quite common for most of the real world products. So that's the demand curve, and we will then can transfer this knowledge to the transportation services. In our previous slides, we mentioned that the transportation can be considered as an economic goods, and the demand of the transportation will be can be evaluated as the traffic flow on the network. And also, we define that demand transportation is a derivative demand, so it does not have any value to the self. It's only related to any desired activities. So those would be some assumptions we made for the transportation service. And with that, we can consider the a product, a real world actual product, say that an apple. We say that the at location A, there's a demand curve about the quantity that we're gonna consume. Say that there will be 10 tons of the apples that we want to consume at location A at some price. And of course, this amount is decreasing with the price of the products. If we increase the per pound price of the apple, then definitely the quantity that you can consume will be smaller. So The red line here shows the relationship between the quantity and the price. So this is about location A. And what at location A with one price, we have one quantity. But if we consider a case, a transportation service, say that there's also some demand at location B, and location B is about certain distance away from the location A. And if we want to transport the product from A to B, you need to spend some actual cost, which will be the cost of the transportation. If we define the cost of transportation as a CAB, we will in that sense, the price at location B should be PA plus CAB. So it's the price at A plus the transportation cost. And now you can then determine that the quantity of the product at the point B, well, it definitely is a function of the price. And as the price at B is the price of A plus the transporting cost, so it's just a function of the A, PA plus CAB. And we can then go to see more details about what's the how we can identify CAB and how we can find out the quantity at the point B. Assuming that you have the transporting cost of CAB, which is this amount of value. So if the price at the point A is PA, then the price at the point B is PA plus CAB. So assuming that the demand functions about the cost and about quantity and the price will be the same at A and B, then you will observe that at the point B, the amount that it should achieve is QB. And but indeed the price at the point A, is PA. So what you will observe, like if we have the price of PA at the point A, then the quantity that you're going to observe will be QB at the point B, with the consideration of the transporting cost of the CAB. And if you go to check the points, check all the price, and considering all different cost of the transportations, you will have another line, which would be a solid line here. That will be the demand curve at the point B. It shows the demand, the quantity that we consumed at the point B as a function of the unit price at the point A. And we also know that the volume at the point B, it's because all the products transport from A to B, so the volume at the point B is only determined by the QPB, which would be the demand, the quantity and the price relationship. And as PB is in the function, it's PB equal to PA plus CAB. So we can say that the volume, once if you know the demand function, what's demand function at the point A, you know the price of the point A, then you will be able to use these two knowledges to identify what's the volume from point A to point B to transport that specific good. So this is the one that we can conclude from the for the demand of the transportation with respect to the price at one location. And so this is just one product, but if we want to have more information, as we just mentioned previously, volume is a function of the PA and QA, and it can also be in a function. It can also be determined by the if we are given with the one value of the product PA, then the volume should be in a function of the cost of the transportation. And of course, with a higher value of the higher cost of transportation, the volume from A to B will be smaller. So that's the reason you're going to observe a decreasing curve about relationship of VAB and CAB. And in addition, if you increase the value of PA. If the price at a point location A is increasing, of course you're going to observe smaller value of the volumes from A to B. So that's what you're going to observe about decreasing VAB by increasing PA. And this is the part that we analyze about the demand of the transportation as an economic good. And the next thing we need to think about is how we're gonna analyze them and using this information to estimate the demand of the transportation and also the supply to determine the price with respect to the volume. So that will be related to the microeconomic demand theory. And it actually includes two parts, the consumer demand and the market demand. The consumer demand will basically consider the disaggregate demand theory, where we will try to understand the behaviors of each individual users. And the market demand will be related to the overall market, what's the aggregate features of the demand and the cost. So we're going to go through them one by one. First, let's go to check the consumer demand theory. For the consumer demand theory, we will have some assumptions, which will be the common assumptions applied for most of the products. First of all, we should say that there always exist some choices. If we want to go to purchase, let's just go to the general case. If we want to purchase some products like the fruit, you can choose the apple, you can choose the orange, you can choose watermelon, you can choose strawberry, and so on. So you always have the choice. And if we are talking about the transportation services from location A to location B, you probably can choose route 1, you can choose route 2, and route 3, and so on. So this is the first assumption. If there's only one choice, then the problem will be very simple, and no matter it's only determined by your demand, how many products you want. It does not relate to transportation, because no matter what kind of demand you have, what kind of cost of the trip you need to pay, it must go through that trip. So we will always consider the choice. There will be some choice there to understand the consumer demand theory. So that's the first thing. And the second thing is about the utility. So we will have the utility function to simplify the commodities, and we will also have some define the utility function to determine whether you want to take the trip or not. And the third, there will be some consistent preferences structures. So if you prefer X over Y, and also you prefer Y over Z, then based on this kind of preferences sequence, you will prefer X over Z. You will not have the other situation Z over X. So that not happens. So your preferences is always consistent. So that's the third assumption. And this first one is the insatiable consumer. So basically assume that most of the consumers are very greedy. They always want to get more products, and they always want to spend less money to get the optimal amount of the products they can take. And this last one is the budget constraint. So as the consumer, they may not have infinite budget. Instead, they will have a limited amount of the money they can spend to purchase those products. So those would be the 5 assumptions we made for the consumer demand theory. And some of them will be explained with more details in the next few slides. Here, first of all, let's consider the most simple case. There will be 2 goods, X and Y. And we use letter X and letter Y to define the amount or the quantity we will consume for each product for X and Y. And now for the let's consider a specific case. We have letter x amount of the at the choice of m, we choose x amount of the first product and y amount of the second products. Then this is your current choice. And now we will be able to define the utility at the choice m. So the utility of at the choice m is related to the amount of the x and y. So it's the function of letter x and letter y. And we say that this is the utility of m as u star. And then we can define the region in this x and y plane for all the points. For all the points in the yellow region, is called the preferred region. So which means that for any points here, I just say that this is a point n with xn, yn. So xn is higher than x, yn is higher than y. So with these two conditions, for any rational users, they're gonna take the point n instead of m, because they will always get more products in both x and x and y. So that's one. That's called the preferred region. And of course, we have another region which is not a preferred region. Say that this is the region. There's the one point k, and have the xk, yk. So xk is always smaller than x, yk is always smaller than y. So as the very rational consumer, you will never take any point in the now preferred region over the point m, over the choice m. So this would be the two regions we defined, the preferred and the non-preferred region. And if we take 2 points, point P in the preferred region and point N as non-preferred region. And definitely we can observe that the utility at the point P is higher than M and is higher than N. So this is what we get. UP is larger than UM, is larger than UN. And of course we can then draw a line. If we draw a straight line to connect these 2 points from P to N, you will see that the utility is gradually decreasing along the line, right? Because P is the highest one and N along this line, P is the highest one, N is the smallest one. So it's gradually decreasing from P to N. And we know that P is higher than UM and the UN is smaller than UM. So you must be able to find out the point, which you define as point M prime. At the point M prime, you will be able to identify that the utility at M prime is the same to the utility at the point M. So that's what we can sure. It's like there's a point M prime with utility of M prime equal to UM, which will equal to U star, as what we defined previously. And in that case, we will say that the consumer for that specific consumer, there isn't any difference between M prime and M. So the utility for these 2 points is the same to that consumer. And of course, if we go to check the other possible solutions, you can find out a lot of different points, similar points to M prime. So if we put all these points together, all the points with the same utility to the M together, it will eventually draw a curve with the utility equal to U star. And this curve is called the indifference curve. This is one of the very important concepts we have to define in this class. We're going to use this indifference curve, or we see that IC, to find out the optimal amount of the X and the Y products for each consumer. And so that's the definitions of the indifference curve. And now let's go to see some properties about the indifference curve. First of all, we have to understand that the products is for all the products, all the consumers, they will be in the insatiable consumers, which means that they follow the diminishing return rule. So this rule indeed shows that the utility function is a monetary increasing function, but there will be some conditions for this function. First of all, if we go to check the first order derivative, du over dx is always positive, means that the function is increasing over the value of x. With a higher value of x, the utility would be larger. But it also has a second condition. The second order derivative of the utility function is less than 0, means that if we already have more products, then the utility that we can further gain by get an additional product will be smaller. For example, if you have the if you only have one product on your hand and you get another one, so from 1 to 2, the utility gain will be very large. Say that the amount of 10. But if you already have 100 products in your stock and you get another one from 100 to 101, then the utility gain will be very small, probably only increase from 200 to 201, something like that. So these two conditions is the most important features about the insatiable consumers. So their utility should satisfy the first order derivative positive, second order derivative negative. So that's the first rule we're going to get. And then we can summarize the properties about the indifference curve. Another thing we also want to know is like for the two products, X and Y, they will actually be independent to each other. So if we have X amount of the first product, Y amount of the second product, the total utility could be the utility of the X plus the utility of Y. So these two are independent to each other. So there aren't any joint functions between X for X and Y simultaneously. So uxy will just be u1x plus u2y. u1 is the utility of x, and u2 is the utility of y. And with that, you can find out the second order derivative, not second order, the Hessian's matrix for the two variable functions, and with that, you can find out the Hessian matrix will be the determinant of the Hessian matrix would be positive because you have the value of the second order derivative of u1 be negative, and the also for the second one is also negative, for y is also negative, and x and y are independent, so the joint derivative will be 0. And with that, you can find out the absolute determinant of h is positive, and this gives you the if you find that the determinant of the Hessian matrix is positive, it means that the function uxy is a convex function. This because the value is this kind of the determinant of h is positive, and then you can draw the general curve, indifference curve at the xy domain. So this is a kind of the general uxy function, and if uxy is a constant, then you will have this convex curve, and along this curve, the value of u will be the same. And of course, you can find out multiple indifference curve with different utility values. And from outside, from top to bottom, you will see the decreasing of the utilities. So for the say that the first one is I1, the utility is I1, second one is I2, I3, until you go to IN, you will actually observe that I1 is larger than I2, is larger than I3, larger than IN. So this is the features of the utility function, indifference curve. And we call all these curves together as the iso utility curve. And this iso utility curve, we will use this one a lot in transport system to find out the optimal solutions of the flow. And another thing we want to explore from the iso utility curve is identifying the elasticity. So we say that for this case, it's called the substitution effect. So for one iso utility curve, say that the utility curve equal to I2 for this one. Is in the convex curve, and you can also observe that the first order derivative between y and x along this curve would be negative. It's a decreasing function, and this one actually represents the marginal rate of the substitution, which indicates that what's the changes of the y with respect to the smaller change of the x. And along the same indifference curve, we know that uxy is constant, so we can then derive that duxy along this curve is 0. This is the property of the constant in calculus. And with that derivation, you will eventually get the get this equation. This indicates that the marginal rate of the substitution, so it's dy over dx, would be the negative inverse of the ratio of the marginal utility. So if we know the function of u with respect to x and y, it will be quite easy for you to see how the what's the value of dy over dx along the constant utility. So that's the second feature of the indifference curve. And this conclusion can also be applied to more than 2 products. If you have m products, it will still have the conclusion partial u over partial xm for the product m over partial u divided by partial xr for the product r equal to minus dxr over dxm. So it's the inverse of the marginal rate of the substitution. So this is the property we derived from the indifference curve. And now we need to consider another constraint, which would be budget constraint. Budget constraint is very important in the economic theory. We always need to think about what's the budget we can use for the products to purchase those products. So here, let's consider in a general case with n products, and we know the value as x1, x2 until you get xn. And this will represent the n different products. We know also know their price, P1, P2, and Pn. And the total budget is set as capital B. So this is the assumption. We want to use this, if we are provided this budget, and for the economic theory, we want to make sure that all the money spent should be less than the budget, which means that for the consumption x1, x2, xn, pi times xi, which would be the money spent for the product I. If we sum them together, they should be less than the budget, less than or equal to the budget. And for the to find out the optimal solutions of the consumptions for each product, we want to maximize the utility. As a greedy consumer, we also want to maximize the utility. And the constraint condition is like the total money you spend should be less than the budget. But as you know that the consumers will be in the insatiable consumer, so it means that if you have $100 for you to spend, and as an insatiable consumer, you will always want to spend all the $100 to maximize their utility. So in that case, we can just simply replace the sign smaller than or equal to the equal sign, which can simplify our optimization problem. And this would be the revised optimization problem for us to find out the optimal consumption with respect to maximizing the utility. And now solving this kind of optimizing problem would be relatively straightforward. I believe you have all learned the Lagrangian multiplier to solve the optimization problem. So first of all, what you need to do is like you are trying to maximize introduce the Lagrangian multiplier lambda, and for the constraint, it will just be the summation of pi times xi minus b. In this case, for the ideal situation, this content should be optimal situation. This content should be 0, so there's no difference for you to find out the maximum value of the utility. And then to find out the maximization of zx lambda, lambda here is the Lagrangian multiplier, and x represent the consumption for the n products x1, x2 to xn. What you need to do is just to find out the first order derivative with respect to x and y, x and lambda. So at the optimal values of the x and lambda, the value should be 0. So we have partial z over partial xi equal to 0. And partial z over partial lambda will also be 0. And if you apply this equation back to these two optimization conditions, you will find out the partial u, the first kind of for the consumer I, you have partial u over partial xi plus lambda times pi equal to 0. And you can also find out the equations for the other products. And eventually you can derive the relationship. I will skip the process about how the conclusion is derived. You can, if you are interested, you can go through the slides about the detailed steps. So eventually we can find that at the optimum solution, at the optimum value of x and lambda, we have partial u over partial I divided by partial u over partial xj will equal to pi divided by pj. So this indicates that the this will be actually consistent with the conclusion we made previously. The marginal rate of the substitution will be the minus inverse of the ratio of the two first partial derivatives. So this is the case that is consistent with what we have already derived. And with that, we can simply further simplify this conclusion. So this will indicate that the ratio of dx and dxi and dxj will be related to the ratio of pi and pj. So basically, you can see that the marginal rate of the substitution will be the negative inverse of the ratio for their price. So this will be very straightforward, and you can use this one to quickly find out the solution for this optimization problem with the budget constraint. And with that, we have the conclusion. At optimal, the optimal consumption vector is chosen such that the marginal rate of the substitution of any products is equal to the inverse ratio of their price. So that's what we conclude. And of course, here I just give in a simple figure to show you what's the how we can get the optimal values from the multivariate function. So basically, at the smallest value, you want to make sure that the first partial f partial x equal to 0, partial f partial y equal to 0. And now let's check one example to see how we can handle the solve the problem with the budget constraints. Here we consider two products, x1, x2, and we know their price as P1 and P2. And we have the budget constraint as B. The total budget is capital B, so P1 times x1 plus P2 times x2 will be capital B. And with that, we can draw the budget line from the x1, x2 plan. So this is the as B is the budget, the constant budget. So we can draw a straight line to connect the to represent the budget constraint. So if x1 equal to for x1 equal to 0, you can find out x2 equal to B divided by P2. And for x2 equal to 0, you can find out x1 equal to B divided by P1. So that will be the two ends of the line. And you will also have the relationship as dx2 divided by dx1 equal to minus P1 divided by P2, which will be the slope of this line. So the slope of this line is minus P1 divided by P2. And for any points in this behind this line, in this yellow region, we define them as the feasible region. If there's any point above this line, it means that the budget will be higher than B. Only for the points within this yellow region, it means that the budget is less than the value of B. But of course, we want to find out the solution along the straight line, along the black line, which can help us to fully utilize the budget. And now we can then integrate the budget constraint with the ISO utility curves. So we have for these two products, we have settled the ISO utility curves, and this will be one value. So say that U1, and for this curve, you cannot find out they are all outside of the outside of the feasible region. So it means that any solutions along this line is not feasible. So you need to check the other ISO utility curves, and you can gradually decrease the utility. Eventually you can find out in a line. ISO utility curve, which will be tangent to the budget constraint line, and with that, this point, the tangent point, will give you the optimal consumption, which will give you the highest utility, and with the feasible solutions. And this is the point we need to select, which is also the optimal solution. We see that the point is x1 star and x2 star. And again, it will give you the optimal, the highest utility as U star. So this is the general steps for you to find out the optimal solution with two products. And the next, we're going to consider some more complicated situation. Say that at the beginning you have the budget of B, capital B. What happens if your budget increase from B to B prime? In that case, well, this usually comes from the increase of the incomes. If you have higher incomes, then your you will have a lot more budget to spend. So in this case, you need to define a new optimal point to maximize the utility with the increased budget. So for the budget constraint, well, again, you can see the budget constraint in this figure, and you can find out the optimal solution x1 star and x2 star. But with the new budget constraint, you will have higher value as b prime. Then you will get a new budget. You will get a new budget line. But here you can see that as the price of the two products is not changing for these two situations, so the slope of the budget line will still be the same. They only move parallelly at a certain distance. So with the increased budget constraint, we will have a new budget line, and at the new budget line, you will also have a new optimal solution. And let's say this is a x1 star prime and x2 star prime, and the changes from x1 star to x1 star prime and also from x2 star to x2 star prime is defined as the income effect, how the income will change the consumptions of the two products. And this is about the impact of the budget. Another thing we need to think about, which is quite common in reality, is the effect of the price. What if we change the price of one product? How the optimal solution is changed over by this modification? For example, we assume that if the product 1, the price is reduced from P1 to P1 prime, and we still have the same budget. The budget is still capital B. Then we can see the new budget plan, new budget constraint. If we do make a comparison about the two budget constraints, you can see that the slope will be different. For the first one, the slope is minus P1 divided by P2. The second one would be minus P2 divided by P1. The second one would be minus P2 divided by P1 prime, which would be, well, I guess I'm wrong. The first one is minus P1 divided by P2. And the second one would be minus P1 prime divided by P2. So apparently this one is smaller than the first one. So if we put them together, in the same figure, you can check the difference about the two budget constraints. And of course, you can also find out the new optimal solution for the new budget plan, and say that this is the another optimal solution, x1 star prime and x2 star prime. And with that, you will see how the solution, the optimal solution, is changing over the time, over this the modification. But for this case, the changes can be categorized or divided into two parts. The first one comes from the substitution. The second one comes from the effect. The substitution means that the changes caused by the price change without considering the budget. The second one shows the changes in the with respect to the budget. So to identify the substitution effect, what you need to do is like you will need to move the new budget line, the new budget constraint, to the position which will be tangent to the original isolated curve with the original solution. So at this point, it will have the same utility to the one at x1 prime and x2 prime. And from this point, from the original solution to this point, is called the substitution effect. And then from this new point to the final optimal point, it's called the income effect. So that's the two parts we defined for the effect of the price. One is the substitution effect, the other one is the income effect. So that's the by combining them together, that will be the total effect. So that's the how we define for the normal products. And in reality, there are also some interior products. These are not the inferior products. And this one is quite different from the regular products we defined. Usually for the regular products, say that you have the higher income, you probably will purchase more products. But for the inferior goods or the inferior products, it's different. If we have, for this kind of goods, if we have higher income, you probably will purchase less for the inferior goods. This is a little bit counterintuitive, but it happens a lot in reality. One typical example is about the fast food. So for the fast food, the price is pretty low. And if your income is low, you probably will go to the fast food restaurant a lot. But once with your higher income levels, you will probably go to some fine restaurant. And with that, you will have less consumptions about the fast food. And this also applies to the some famous examples about the coffees. You can purchase the coffee from the McDonald's could be considered as the inferior goods. You have, if your income level is low, you probably will purchase more coffee from the McDonald's. But if once your income increase, you will probably prefer to go to Starbucks or some high-end coffee shop. So this will be just some examples about the inferior goods. Basically, you will be able to find out those examples in our daily lives. So for the inferior goods, the iso-utility curve will be very different from the normal products. The figure here shows some typical iso-utility curve for the inferior goods. With that, you can see that if we decrease the price of the product one, say that you decrease the price from P1 to P1 prime, and you can then draw a new line. Say that draw a new budget line. With that, you can see that instead of increasing at the optimal solution, instead of increasing the consumption for P1, you will see the reduced consumption of X1. And of course, you can see the increased consumption of X2. And this is if this happens, we will say that this goods is the inferior goods. And decreasing the price of one products will result in the less consumptions of the same products. With that, we will have the definitions of inferior products. And if we want to go to see more details about the inferior products, we can then go to check what's the substitution effect and what's the income effect. For the substitution effect, you can see that it actually increase the consumption of X1 by reducing the price. But if we go to check the income effect will have the much higher reductions compared with the increased effect from the substitution effect. So for the total effect, you will observe the reduced values about the x1. And this happens when the income effects overwhelms the substitution effects, and you're gonna observe the smaller amount of the consumptions for the one with the reduced price. So that would be all about the consumer demand theory, and with that, I think I can just stop here for some questions, and we can, if we don't have any questions, we're gonna wait for taking a break for 10 minutes, and okay. So I see some questions. So the so for the, I see from questions from Xiaoyan about the utility. Yes, there will be some examples about the utility. Utility will represent, it's hard to quantify, but there will be some function to represent how you're going to value the activity. We're going to have some examples about the utility functions with respect to the different products in the next slide, lecture 4. And with that, you can see how we're going to use utility for the calculation. The Ali has a question about the Hessian matrix, and the Hessian matrix is similar to the second order derivative for the single variable functions. So the Hessian matrix is basically applied for the multivariate functions. For the multivariate functions, if we want to determine the second order derivative, you cannot get the partial u, say that the partial u over partial square u over partial x squared directly. Instead, you need to consider the cross differentiations, and the Hessian matrix will show you all these possible direct and cross differentiations for multivariate functions. And usually if the determinant of the Hessian matrix is positive, it means that it's a convex function. If it's negative, it means that it's concave function. Jing has the questions about the ISO utility curve in page 29. So basically for the ISO utility curve, are you talking about 29 or the definition of the ISO utility curve?
Just this page.
So the definition of the ISO utility curve is in the previous actually in the previous pages, but ISO utility curve means the so each indifference curve represents one ISO utility curve. These two are equivalent to each other. So the ISO utility for one ISO utility curve, it indicates that the for any points along the curve, like for this example, you have two products x1, x2. So for any point here, let me try to. For any point, along this curve, you may have different combinations. So this is x1, x2, and this is x1 prime, x2 prime, x3 prime, x4 prime. So those would be different combinations of x1, x2. But if you put them in the utility function, uxy, they will all give you the same value. Say that u1, they all give you the same value of u1. So ux1, y1 will equal to ux2, y2, ux3, y3, and so on equal to u1. And that's for one indifference curve, or we say that ISO utility curve. And for the second one, if you go to another one, say that this is U2, then you will have different points, and along this point, you will get the utility. All of them will have the same utility. The value will be U2, and similarly for U3, U4, and U5. And basically, if we have if you check all this isoutility curve from top to bottom, you will see that the value is decreasing. So U1 is higher than U2 and U3 and U4, and until you get a UN. And for the problem with the budget constraint, we definitely want to find out the sum one, which can tangent to this budget line. At this point, you will have say this point is a x1 star and the y1 star, x2 star. I'm sorry, this is a x2. Well, I guess I just put it wrong. So this is a x1 prime, x2 prime, something like that. Yeah. So back to this point. So we have x1 prime, x1 star, x2 star. So the utility say that it's a u star. So you have u x1 star, x2 star equal to u star. This is the utility, the optimal utility get. And also you will have P1 x1 star plus P2 x2 star equal to B, because it's along the budget constraint. So all the points along the budget constraint, you will have the same budget B. If we continue searching something, find another utility curve. So this would be the U star prime. You will find that there might be many possible solutions within the yellow region. Those are all possible solutions, but you can see that their utility will be U star prime is always smaller than U star. So for the optimization problem, we want to maximize the U star, the utility function, and with that, this tangent point will give you the highest utility, and that's our solution. And it's the good thing is that it only has one solution, so it's the unique solution, and it's always good for us to remove any confusions from the optimization problem. Okay. Okay. Do you have any questions? If no, then I'm gonna take a break. So now it's 4:13, and let's resume our lecture at 4:23. Okay. With that, I'm gonna turn off my camera and mute myself. Also, I need to charge my computer. Okay, let's resume the lecture today, and I probably will not be able to check your messages in the during the lecture because there's only the other computer is a little bit far away to my desk. But if you have any questions during the lecture, you feel free to open your mic and interrupt me, and we're gonna have some discussion about it. Unless the question would be some complicated one, we can save it for the end of the lecture. So don't be shy about asking questions. It's a small class, and we will try to make it flexible so that if you have any questions, you can bring immediately. Okay. So I will continue the new lecture. This is about some introductions about the market demand theory, wrap up of the market demand theory and the consumer demand theory, and how they're going to be applied for the determination of the demand functions and supply functions, and then eventually we will get the equilibrium to find out the optimal solution or the best values for different products and also the traffic volume. So first of all, let me go to check the one moment, just a moment. So let me double check it. Just a moment, let me try another one. Let me disable my sharing first and then resharing my screen. Okay. Now let's go to check the market demand. So the market demand will try to analyze the aggregate relationship between the trips and the cost and also the income levels. It will talk about the overall amount of the trips in the whole market or the population. But first of all, let's go to as we have already introduced the consumer demand theory, we will try to review what's the relationship between the market demand theory and the consumer demand functions. We will start with the linear relationship. So this actually applies for a lot of travel demand analysis. For the linear relationship, we assume that the number of the trips in the city is a function of the population and also the income levels. So here it's a little bit different from the previous one. And regarding to, the P here represents the price. Sorry. So P is the price and I is the income level. And T is the trips. So this is the value for the entire city. But if we go to check each individual consumer, say that the consumer K, we will still have the linear relationship, but the value of the P and I will be different because the price might be different for each individual. The income of each individual might be different, and they may have a different number of the trips. So this is the this would be the individual, obviously the consumer demand function, and if we are talking about in a city with the population size of n, then I find out the relationship between T, the total number of the trips, and the value of TK, which would be trip generated by each individual. So with that, capital T will be the summation of TK, and which will also obviously be the summation of the linear equation. And with based on this one, you can make some simplification about the linear equation. So what we get is like for the m, for the population size of n, t will equal to n times alpha 0 plus alpha 1 times the summation of pk plus alpha 2 times the summation of ik. So that will be the total price and the total income for the whole population. And you can also find out the average values of P and average value of the income. So with this one, we can further simplify the linear equation. So capital T will be alpha 0 prime plus alpha 1 prime P bar plus alpha 2 prime I bar. So alpha 0 prime will be n times alpha 0. Alpha 1 would be alpha 1 prime would be alpha 1 times n. Alpha 2 prime would be alpha 2 times n. So that's the revised equation, linear equation for the whole population. And the P bar and I bar here will represent the populational mean about the price and income. And if we start with the case, say that the price, usually for one product, the price is constant for all populations in the city. This will not be changed with respect to the to each individual. So if say that P is the same for all the population, then P prime will just be P. The only thing we need to think about is the average income. The income for individual might be different, but over here we want to consider the average income of the entire city. And then based on this information, we can then find out the elasticity, especially the price elasticity and income elasticity for the demand functions. So from this equation, we can identify the number of the trips as a function of the price and also the income. And with that, we can then estimate that by searching the optimal solutions, we can find out the demand of the product I would be the function of the price, for all the products, and also the budget plan. This actually comes from the previous optimization problem. And this one can be the individual, can be the demand for the consumer K, for the individual K. And we will also define another variable xi as the market demand, which would be the consumption of all the consumers in the city. And apparently xi will be the summation of the xik. So this is what we conclude about the relationship between the market demand and the consumer demand. Basically, one is about the individual, the other one is about the whole system. And then with this information, we can calculate the elasticity of the good I with respect to the price of the good J. So this one requires us to find out the definition of the elasticity. So we use the notation EIJ to represent the this elasticity of the product I with respect to the price of the product J. So that is the pressure Xi divided by Xi divided by pressure Pj divided by Pj. So this is actually a definition of the elasticity. And now we can make some further derivations by introducing the individual demand by doing some further analysis. Again, I'm going to skip in the details about the derivation. So eventually, you can find out in a very simple equation. So for the finalized analysis, you can find that the elasticity of the EIJ will be the weighted elasticity of EIJ for the consumer K, for each consumer. So this is like the aggregate demand price elasticity will be the weighted sum of the individual consumer elasticity with respect to the amount they obtained for each product for the product I. So that's the price elasticity, and we can also do some analysis about the income elasticity. So here we use this symbol II to represent the income elasticity. Was again comes from the definition of the elasticity, and here we make another assumption, define another value, AK, to represent the portion of the total income associated with the market segment K. So this one is actually defined. So K here will represent the individual, or for the future, it can also be represent a group of the person. But let's make it simple as the individual, each individual consumer. And for the features, we have the summation of the AK will be 1. And then by introducing this new variable, we can do some derivation. Again, I'm going to skip in the derivation. So eventually, you will find out another variable, another relationship about the aggregate income elasticity and the individual income elasticity. So the final solution shows that the aggregate demand income elasticity is also the weighted sum of the individual consumer income elasticity. So the weight is also determined by the amount of the products purchased by the each individual consumer. So that's the two features about the elasticity to show the relationship between the market demand theory and consumer demand theory. And following by that, we will have more analysis about the consumer demand. So this will be the some continuation about the previous analysis with respect to the optimization for the budget constraints. So we have the budget constraints to maximize the utility of a set of the products, and again, as we based on this optimization, we can find that the value of xi will be determined by three variables. The first one is the price of all the products. The second one is the total budget you have to spend. And the last one is the format of the utility function. And again, you can see that for the utility function, it is related to the amount of the other products that you have consumed. So this is actually a very complicated equation, but we can make it simple, just assume that xi is the function of the p, b, and the utility function. And also we can use the solve the optimization problem and find that under the optimal consumption pattern, the utility function is just determined by, if you go to check all this all the n optimization, all the n equations, you can find that the utility function is a function, it's a certain function of the price. So by getting this conclusion, we can simplify the consumer demand function and say that the consumption of the product I is just the function of the price of all the other products as well as the total budget you have to spend. And this gives us another hint about the determination of the consumer demand function. So in order for you to determine the consumer demand, you are not only need to know your own price, you also need to know what's the price of your competitive goods. For example, if you very simple example, it's like if you have $10, you want to purchase some apples and oranges, and you want to purchase as much as possible, then you not only need to know what's the price of the apple, you also have to know what's the price of the orange. And actually, these two prices will affect the amount of the apple and oranges you have to purchase with your budget, within your $10 budget. This is it's also intuitively true in reality. And with the consumer demand functions, we can find out the cost consumption curve, and it's going to show how the values of xi is changing with respect to the price for the fixed value of the other variables. For example, this cost consumption curves will show, well, for the previous example about the apple and the orange, the cost consumption curve will show what's the unit of what's the amount of the apple you're going to purchase with respect to the changes of the price for the apple, by assuming that the other variables are constant, assuming that the price of the orange is constant, the budget is also constant. And now let's go to see how we can determine the cost consumption curve. So we're going to start with the budget constraint and the ISO utility curves. And by changing the price, you can find out the different optimization values with respect to the ISO utility curve. And with a lot of different price you set for the product 1, so we have P1 smaller than P1 prime, P1 double prime, and P1 triple prime, and it has 4 different values: X1 star, X1 star prime, X1 star double prime, X1 star triple prime. And now if we connect all these points together and draw them in the price and the consumption plan, for each price you have one value of the x1, and you put all these points you obtained from the figure above. You can then draw this cost consumption curve, and this is the one we have to maintain to identify the optimal solution for the optimal assignment for the values of different products within the budget. And we will also have some materials collected for the characters of the consumer demand functions. For the consumer demand, we know that it's a function of the price and the total budget. And also we know that the budget is related to the income level. So we can, well, for this general function, we can replace the budget with the income. And so the consumer is now the function of the price of all the products and the income levels of the entire population. And now we will be able to find out the elasticity, which will show the ratio of the percentage change in the demand for one product with respect to the to any independent variables. So this is the elasticity we defined previously. And if the if we find that the elasticity for the variable v is larger, the absolute value is larger than 1, then we see that that region is elastic. If it's less than 1, we say that it's inelastic. So inelastic means that the changes of the variable v will result in the very small changes of the volume or the demand. So for the price elasticity, we will try to check the price of the product I, and if we check the price elasticity for the same products, then this is called the direct elasticity. And also we can check the income elasticity as we showed previously. For the direct elasticity, I'm going to show what's the percentage changes of the price with respect to the percentage changes of the demand for the same products. And of course, we have something called the cross elasticity, which will show the demand of one product with respect to price of another products. This would be the definitions about the cross elasticity, cross income elasticity. So we have the symbol EIJ to represent the demand of the product I with respect to the price of the product J. And so this would be some key measurements we have to consider. And with that, we can consider some basic relationship between the consumer demand functions and the elasticity. First of all, we have the budget constraint. And let's see how the budget constraint can help us to simplify the relationship between the demand function and the elasticity. For the in the budget constraint, we know that the amount xi is the function of the price and also the budget. If we put it there, we can then try to find out the first order derivative with respect to the demand, to the budget. On the right side, the budget is constant, so the value is always 1. And if we do some further derivation, eventually, again, I'm skipping the I'm skipping the steps again. So here you can find that the based on the derivation, the whole equation can be simplified as the summation of SI times I equal to 1. And II here is the income elasticity, and SI is the shared budget spent on XI, which means what's the amount of the budget you spend to purchase the product I. And if we do the summation about the SI times II, it will always be 1. This actually comes from the budget constraint. So we see that the weighted sum of the income elasticity is always 1. So that's the that's the first relationship we have to consider. And for the second one, if we consider the differentiation of the budget constraint with respect to the price I instead of the budget, you will find out another interesting relationship. So we do the first order derivation about the PJ on both sides of the of this equation. On the right side, you know that B is the budget, and the budget is not related to the price. So partial B over partial PJ is always 0, and you can do some further derivation on the right side. On the left side, try to do some expansion and simplification. Well, again, I'm trying to skip these steps. So once you complete all these steps and do the simplification, you will find that the weighted sum of the elasticity of the demand for all the products with respect to the price of the particular goods is equal to the proportion of the income spent on the goods. So here, SI and SJ will represent the share of the budget spent on the product J and product I respectively, and EIJ will represent the cross elasticity for the demand of the I with respect to the price of J. So with these three variables, you can get this simplified weighted sum conclusion about the elasticity, especially the cross elasticity. So this is the another relationship, and now let's get to see some common, or we say that some typical demand functions, empirical demand functions. Here I list the three different demand functions: the linear one, the multiplicative one, and exponential one. All of them can be well, even though the original form is not in the linear format, but they can rewritten into the linear format. So for the linear equation, so the in this function, the flow is the linear function of the price and income. And for the multiplicative function, t will be the alpha 0 times p to the power alpha 1 times I to the power alpha 2. If you do the log operation on both sides, you can convert them to the linear format. And for the exponential function, so t is just the exponential about the linear relationship of p and I. And for the second one and third one, do the log operations. Well, you can get a linear relationship with the coefficient of the log alpha 0 plus alpha. The second one is alpha 1 and third one is alpha 2. And similarly, you can find out the linear transformation for the third one. The log t is just a linear equation of p and I. So this would be three empirical demand functions, and with different parameters, you can adapt them for different situations. Again, I say that they can all be written into the linear format. And now let's see some features about the linear demand function. So t equal to alpha 0 plus alpha 1 p plus alpha 2 I. And we want to find out here the capital T is the total number of the trips, and P is the unit cost of the trip. I mean, we now change this one to the transporting example. I is the income about the population, and alpha 0, alpha 1, alpha 2 would be the three parameters. And with that, we can then draw the cost consumption curve with a given value of I. So we assume that the income level is constant. And in this case, when p equal to 0, so the price equal to 0, we get the highest number of the trips. That is alpha 0 plus alpha 2 I. When t equal to 0 means that we have the highest price. So this is for the case t equal to 0. And the highest price we obtain is minus alpha 0 plus alpha 2I divided by alpha 1. So this is the linear cost consumption curve. And we can then find out the elasticity with respect to the price. So if we do follow the definitions about the elasticity, and with that, you can find the elasticity of the linear format, linear equation is alpha 1 times p divided by t. Alpha 1 is the constant parameter, p is the price, t is the total number of the trips. So it's changing with respect to the value of p and t. So if we have the value of p equal to 0, so which would be a starting point, definitely the elasticity will be 0. And if we have the t equal to 0, which will be the end point, the elasticity will be infinite. And we can also find out where the point of elasticity equal to 1. Basically, for the linear for the linear equation, it's usually set as the midpoint of the line. To find out that this point, let's first start with the calculation of the slope of the line. For the slope of the line, it's also straightforward. Just if we go to check these two values, you can find out the slope of the line is minus alpha 1 for this line. And you can also go to check what's the slope of any line of the line to connect it from the origin to any point in the line. Say that the point A with the value of P and T. So with that, we can find out the slope from O to A as M2, which is quickly calculated as T divided by P. And now if we put all these three equations together, you can find that EP will be minus M1 divided by M2. So that's the way for you to define the elasticity based on the slope of these two lines. And what if you consider the line for the point A prime as the midpoint of this line, you can then quickly derive that. I will just skip the derivation analysis steps. You can quickly find that the slope from O to A is a minus alpha 1. So what you can get is the elasticity at the point A prime, it's 1. So here should be here should be I'm sorry, here should be minus 1. So you will find that the at the point A, the elasticity is minus 1. So with that, we can claim that for any points between A and B from the start point to A prime, it's an inelastic region. For any point between A prime and D, it will be in an elastic region, which means that the absolute value of the elasticity is higher than 1. So it means that if you have the small changes in the price, you will have the large changes in the number of the trips. So that's for the linear demand functions. And another thing we need to think about is the point of the maximum expenditure, which also represents the maximum revenue from this function. So our expenditure is defined as the price times the number of the trips. So for this case, that will be P times alpha 0 plus alpha 1 times P squared plus alpha 2 times IP. So if we want to find out the maximum value, just simply find out the first derivative of the expenditure with respect to the price. So if we do this one, and we can quickly find that the optimal value of the P to maximize the expenditure is minus alpha 0 plus alpha 2i divided by 2 times alpha 1. And it's exactly the midpoint that we have to we select from the straight line. And at this point, the revenue is maximized, and we can also find you can quickly find out what's the maximum value from the definition of the expenditure. And so another thing, like if we have the general function, say that if we have general relationship between T and P, say that it's a XP, which will this one is XP. Then we can define expenditure as x times px or p times xp. Either way is fine. And we can then use the first order derivative to find out the maximum expenditure, partial e over partial x equal to 0. And with this one, it can give you the simplified equation. So partial e over partial x will be p times 1 minus ep to the power of minus 1. So this one is related. It indicates that this maximum expenditure is related to the price as well as the elasticity, the price elasticity. And at the maximum expenditure here, if you can quickly find that at the maximum expenditure, P prime EP should be minus 1. At that sense, the you will get the value of partial E over partial X be 0. And this actually applies. This actually applies for all situations, for all general situations, not only for the linear function, for all kind of the demand functions. And we can also do the similar process about the multiplicative functions. So we have the examples of t equal to alpha 0 times p to the power alpha 1 times I to the power alpha 2. And of course, we have some specific definitions about alpha 1 here is less than 0. With that, we can draw the cost consumption curve with the given I values and find out what's the price elasticity. If you follow the definitions of the elasticity, you can quickly get the result as a constant value. So the price elasticity is alpha 1 for this case. It's a constant along all the points in this curve. And for the third one, we can apply the similar process. First of all, let's draw the cost consumption curve with respect to the given value of I. And for this case, you will find out a starting point. So when p equal to 0, we can find out what's the value of I. That is exponential alpha 0 plus alpha 2I. But you cannot find out the end point because the even if I equal to t equal to 0, I is still not 0. The p is still not 0. So with that we can quickly derive the price elasticity, and still you can get a very simple equation. So the price elasticity is p times alpha 1. And this means that the price elasticity is the linear function of the price. And also you have to know that alpha 1 here is in the parameter and it's constant. And at the point you find out the value of EP, equal to minus 1, then about that will be the inelastic region. Below it will be the elastic region. So that will be the 3 examples about the empirical demand function. And I hope that after the class you can go to check how these values, how the income elasticity is calculated based on the provided formulas. And the next thing we want to conclude or learn is the supply function. We have already learned the demand function. And the next thing we want to identify is the supply function, which will show how we're going to determine the price with respect to the volume. So this is actually the supply function is also called the cost function.
For the generalized cost, we usually will use some monetary cost, the comfort levels, the convenience, the value of the time, or put them together to have a consistent unit. But for the transportation system, we will try to use the travel time, or we use the monetary cost. For the cost function, we will show the relationship between the general output and the system general cost and the system output. The system output will be the flow or the volumes as we estimate. So let's go to check one. I'll give you one example about a highway to define the cost function. Previously, we have showed how to calculate the cost based on the fundamental diagram, and you can see that the cost will increase when the volume is increased at the free flow region, and at the congested region, you decrease the flow and the cost increase. So this is a theoretical cost function from the traffic flow models from fundamental diagram. Also, FHWA has BPR functions, and it shows that the cost is linearly is increasing with respect to the volume. So it shows a formula to identify what's the relationship between the cost and the flow on the road. So this would be the two common cost function for highways. And with the cost function, you can also find out the marginal cost function. This one shows the is just the first order derivative of the cost function. So if we are provided with the cost function, you can easily show what's the marginal cost function. This one will shows what's the potential ratios about increasing the volume with respect to the increase of the cost. So that's the three important definitions about the cost function. And now let's go to see some typical features of the cost function. The first one is the short run function, where we assume that the capacity is fixed. So assuming that there's a highway, you don't have any upgrade about the infrastructures or changes about the geometries of the intersection or the freeway. And with that, the capacity is fixed. But for the long run functions, like if we consider the cost in the next 5 years, 10 years, because there are some, maybe there are some construction projects for that road, then the capacity might be higher in the future. Then the cost function will also be changed with respect to the new construction projects. And still, we can take a look at the freeway examples. Here we will have the cost and the function of the flow, and the CI will be the cost of the ice lane on the road. We will assuming that we will only have one lane first, so we have the cost function as a C1V, but and also the capacity is a Q1. But if we have the expansion about the cost, we have an expansion about the number of the lanes. The number of lanes is increased from Q1 to Q2 by introducing 2 lanes. Then the cost function should be modified a little bit. And for this case, the cost function will be the part which will be lower. For these 2 lines, the portion which will be lower than the other one. Before this point, the one lane road has a better performance, and it will give you smaller cost. So you will take this part, and after this region, the 2 lane roads will give you a smaller cost, and your actual cost was determined by the 2 lane road. So that's the case for the changing capacity or the changing cost function for the long run situations. This is important for the long-term transport planning. But for the short-term analysis, we will more focus on the system supply functions, or we say that link supply functions. So this one will be related to the traffic and the supply characters for the single isolated transport facilities, and then connect them by well, they'll only be connected by the by a particular mode or the particular route, and we don't consider the impact of the other links. So for the link supply functions is only about a road segment, a single road segment from point A to point B, and with that it will only have one cost function. And if we have another two locations, link 2 to connect C and D, then you have another cost function. But these two are, because they are not connected with each other, so they are independent. They have no impact to each other. So this is the fundamental part about the supply functions in transport system. We first need to identify the cost function of each link, which will show as C1V, C2V, C3V, C4V, and so on. And later on, we will have to see what happens if they connect together. Because if you see that in transport system, each route will consist of multiple links. And it's possible that you for two locations, you will have multiple links to connect. You will have multiple choice to take. So in that sense, we need to use the link supply function and try to see how to find out the system supply function with multiple links. So the first example that we consider is a directly connection. So we will connect link 1 and link 2 directly. So we will have the sequential links from A to B and B to C. We know the cost function from A to B as CAB, and the cost function from B to C as CBC. And then for the cost function from CAB from A to C, it will just be the summation of the summation of two so CAB, CAC will just be CAB plus CBC. So that's the cost for the same flow. So showing this figure, you will just add these two lines together. So at the volume equal to 0, the basic cost would be would move from, we'll add this amount. These two amounts will be the same, and at another point, you will add another amount to the one above, and you do the same thing. You do the same thing for all the points together, and then connect those points. This would just be the cost from A to C, and this is the sequential links, the cost of the sequential links. And for the second example, which would be in a parallel case, and from link A, from point A to B, you have two links to connect them, and each one will have the cost function. With that, you need to determine what's the cost function from A to B. This one is a little bit tricky. So let me show you how to determine it. First of all, you are provided with the independent cost function of 1 and 2. So you have C1 and C2. So when this one will then, for the total cost from A to B, this one will then be determined by the assumptions about the traffic assignment. So in the traffic assignment assumption, we will assume there's a user equilibrium. In the user equilibrium, we always assume that all the users will be selfish. They will always need to take the route with the smallest cost. And if there are multiple routes, and if the someone are traveling on the, say that there are two routes, two different options, and there are someone traveling on route 1 and someone traveling on route 2, then their travel time must be the same. So which means that the cost of these two options must be the same. So that's the assumptions about the traffic assignment with the user equilibrium. And then for this case, we will need to see how to form the cost function, the combining cost function of link 1 and 2. First of all, if the cost is if the volume is very low, say that at say that if the volume is very low, it's let me start with one simple case. Say the volume is V1. Then if you take the flow, if the vehicle is taking the link 1, it can get the cost of C1. Let me use P1 to differentiate the one. You can get the cost of P1, and if they take the link 2, you can get the P2. Well, apparently P2 is much larger than P1, so in that case, they will this vehicle will never take all this V1 flow will never take link 2. They can just take link 1 with the smaller cost. And similarly for the second case, for V2, still is much smaller than P2, and until reach to the to this case, to this, I'm just using prime to differentiate them, until reach to this case to V1, to the V1. At V1 you have the flow at the point, you have the cost of C1 from the link 1. You have another cost from link 2, which is also C1, but the with respect to the flow here, it's very small. So in that case, there might be, well, for this specific case, there might be no vehicles taking link 2. But if you increase that one a little bit, then maybe part of them will take link 2, and the part of them will take link 1, and they can all get the same travel time from A to B. And in that sense, you need to add the flow together, add the flow from link 1 and link 2 as the total flow from A to B. So this is what we get. And if the cost is below the minimum cost of the link 2, then you will always take the link 1. But if the cost is higher than the minimum cost of the link 2, then the flow of the cost C2 will be the summation of the two flows. So you can see that the at cost C2, the total flow would be V21 plus V22, and they reach to this point. And again, you can go to the other cost C3, and the total flow for C3 will be V31 plus V32. And then you can go to check all the other points. And eventually, if you put them together, you will get the an updated cost function for these parallel links. So this one is very different from the previous example. about the sequential links. So this is the way for us to update the cost function for the set of the links and the options, other options. And now, if you have identified the cost from A to B, and if we have already defined the demand, well, which will be the volumes on the traveling on the link, and you specify the demand curve, you specify the supply curve, you can then identify what's the actual flow is traveling on that link. For the supply curve, it shows the what's the cost determined as the value of the flow. And from our very first lecture, we can identify that this kind of the shape of this curve, the supply function, is determined by the management strategies and also the investment investment from the government. And for the demand, we also analyze their demand with respect to the price, the cost of the price, the cost of the trip, and also the budget and so on. So for the demand, V is the function of the cost, and for the supply, cost is the function of the V. Those would be the two same variables, and you can put them together. If we can put them together using the equilibrium, put them together, the value, the crossing point is the equilibrium point, where you can get the actual, where is the actual amount of the flow is traveling between A and B with the cost, with the same cost for the supply and demand. And this is just about the typical example. And another thing I want to mention is about the latent demand. So this one will refer to the to some changes about the supply function or the demand function. For example, if we are talking about in the freeway segment, you have the supply function, which would be blue line here, and also you have the demand function, that would be the green line there. And in the next, say that in the next 6 months, the government has some investigation about a new construction project, road construction project, and with that, the supply function will be modified. They will have a higher capacity in the future, and which means that it will pull down the this supply function a little bit. So with the same cost on the road, you can support more volumes, more flows, and this, in that sense, with this kind of investigation, your equilibrium point is changed from A to B, and of course you're gonna see the changed volume from VE to VE prime, and this difference is defined as the latent demand, which would be the demand changes from the changing supply functions. And also the amount of the latent demand is determined by the shape of the demand functions. For different type of the demand, the different shape of demand functions, the latent demand amount will be very different. I'm gonna give you some examples about how the shape of the demand function will affect latent demand. So let's consider. Let's remove the previous example, previous demand function, and change this one with another demand function. This demand function actually comes from the will represent the entertainment. It will be very sensitive at the in median cost. With that, you can see a very significant a very large value about the latent demand. So basically the latent demand, the amount of the latent demand is determined by the elasticity of the demand with respect to the price, or with respect to the cost. And well, here there will be some typical demand shapes applied for the different purpose of the chip in the transport system. For the chip to the work, it's a kind of the mandatory chip. So no matter what kind of cost you have to spend, you must take it. So this indicates that the cost of the chip is the demand of the chip is less sensitive to the cost, and you're gonna see that the value of the demand it's pretty consistent. It's pretty consistent over different value of the cost. And for the shop, this one depends. Sometimes the shopping would be mandatory need to go to some grocery stores to purchase some necessary products for the daily life, and but it depends. The number of the chip can be changed a lot depending on the cost. If the cost is high, then definitely you will have less chip, and if cost is low, it will inspire you to do more chips. So it's the sensitivity is moderate. It's not a very significant, or it's not very low. It's not like the work type of the chip. For the chip to the work, it's mandatory, and for the shop, it's optional. While for the entertainments, it's very different. So people will pay a lot of attention to the cost, the actual cost they have to spend for the chip. For a lot of times, if the cost is acceptable, they will decide to go. If it's high to higher than certain threshold, they won't decide not to go because all these chips are not necessary. So in that sense, it will be very sensitive at a small range of the cost, but for very large and very low cost, the elasticity will be very small. So that's the three type of the chips that we will generally considered in the transport system. But in the transport system, the number of these three type of chips will usually be combined together. So if we put all of them together, you will find out in a joint chip, which will be a joint demand function, which will consist of work, shopping, and entertainment chips. And this chip will definitely not as the chip to the work. It's not which is not elastic. It's definitely not like the entertainment, which is very elastic in the certain value. It's about something between the work and the shop, depending on the portions of the chips in the area. Okay, so with that, I finished all the introductions about the theoretical background of the microeconomic theory. And now let's go to see some examples about how we can use those theoretical analysis to calculate the number of the chips and to find out the optimal solutions for certain realistic scenarios. So first of all, let's go to check on a very simple example. Assuming that we have the utility function. The utility function is determined by the amount of the products that you have purchased or you have consumed. In this case, we only consider two products, x1, x2, and the utility is x1 squared plus x2 cubic. And with this utility function, we can then draw the iso utility curve. So it's in the convex functions, and this figure shows 5 different utility values. That is 20,000, 200,000, 400,000, 600,000, 800,000, and 1 million. With respect to X1 and X2. So this is the ISO utility curves. And each one will represent a fixed utility value. And now we assume that there's a unit price. X1 is $3 and X2 is $4. And also we have the budget of $100. With that, we want to find out what's the optimum value of X1, X2 to maximize the utility, the defined utility function. So with that, we can then first draw the write down the budget constraint. The budget constraint is so budget constraint is a summation of the P, or just Pi xi smaller than or equal to B. We change this one to equal. So for this case, P1 is 3, P2 is 4, so we have 3x1 plus 4x2 equal to 100. And now you can simply get the value of x2. It's 100 minus 3x1 divided by 4. So this is the relationship between x1 and x2, and show the budget constraint. And you can put this one in the utility function. And now the utility function is only the function about x1. And you want to maximize the utility function. So do the differential equation, first order differential equation, and this value should equal to 0. By solving this equation, you get the value of x1 as 13.33, and well, you can then calculate the value of x2 as 15. So that's one way for you to do it. And of course, you can do the other way. You can do the other way with the ISO utility curve, and once you have the budget constraint, you can draw in a straight line, and then gradually reduce the utility values. This is just one example. Gradually reduce the utility values and get an ISO utility curve, and eventually gonna find out the optimal values, the tangent point, and that will be the optimal solutions you can get for the for this specific example. So either way is fine, and this one may give you less accurate result because you need to find out a tangent point. It's not that easy to do it even by computers. Okay, so that's the first simple example about the how to get the optimal solutions with the budget constraints. And and the other thing that you may need to think about is the how to calculate the elasticity. And with this one we have already found out the optimal solution. X1 star is 13.33, X2 is 15, and we can then find out what's the value of the first order partial derivative with respect to X1, X2 at the optimal solution. So for X1 it's 90,000, for X2 it's 120,000. And if you go to check this one, find out the ratio of these two values, you can get the value as 9 divided by 12, which is 3/4. And this is exactly the same to P1 divided by P2. So this is actually verifies our previous assumptions about the marginal ratio of the substitution. It's actually related it's actually the same to the ratio of the first order partial derivative. And so with the budget constraint, and you can get the value, well, as what I explained previously, you can get the value as the optimal value at the tangent point. And for this case, it's around 600,000. And so that's the first example. You can using either method to find out the optimal solution. And for the second example, which will be related to the demand and supply functions. Suppose that the demand for an air travel between two cities, for example, from Ottawa to Hamilton, it follows the linear function. So the demand is determined by the price. If the price is higher, the demand would be larger. So for this case, it's 10,000 minus 50p. So that's the demand. And for the airline, for the side of the airline company, they also need to determine what's the best price to attract or to get the highest revenue. So the in their study, they say that the price is a function. It's also a function of the demand. Well, for the company, if they see a higher demand, they probably will increase the price because they want to get a higher revenue. Here we also assume that it's a linear function, so p equal to 100 plus 0.005 times x. And with that, we want to find out what's the ticket price, what's the optimal ticket price and optimal demand. And with this, I believe the solution would be very simple. The first one is just the demand function, and the second one is the supply function. And if we put them together, draw them in the same figure, the intersection of these two lines will be the optimal solution about the ticket price and the demand. So first, we draw the demand function. It's 10,000 minus 50p. And then we will have the supply function. It's 100 plus 0.005x. And apparently, you can get the intersection. So the result is for the demand, it's 4,000. For the price, it's 120. Also, for this simple example, you can just use the two equations to get the result directly. It's not necessary for to draw the figure. And at the equilibrium, we have the you can then also calculate what's the elasticities with respect to the price. And another thing you can consider is like if you change the price, if you change some parameters, like if you change the parameter from 50p to 40p, what happens about the price and the volume. So that's the second example. And the third example, I will probably want to hold it here because it's a very big problem. I don't think I can finish the all these questions, all the examples today. So I would like to reserve the rest 14 minutes for any potential questions. And let me go to check what's the question you have. Is there any other questions? Okay, so Jing still have the questions on page 29. I hope it's the definition 29 about definition of the aggregate demand. Okay, so in 29, Okay, so I guess you are talking about the demand here. So the aggregate demand here will represent the total demand from the city instead of the if I'm talking about aggregate, it means that the total number of the trips or the total number of the volumes from in this case, probably give you a simple example. In this case, we are talking about point A to point B. So the aggregate demand here will represent how many of the trips from A to B. If we are talking about the disaggregate demand, it will represent individual trip, individual user. Individual user. So say that at point A, there will be, I just assume there's 1,000 population. They may generate, say that 2,000 trips from A to B. Then this 2,000 trips is the aggregate demand. But for the for this 1,000 population, maybe there for one person, there's one person every day it has one trip. There's another person every day. There are two trips, and the third one maybe have four trips. And this kind of 1, 2, 3, and 1.5, 2.5, something like that. This would be the individual trips, and that's the disaggregate demand. So disaggregate indicates how many trips will be generated by each person, and aggregate indicates how many of the trips will be generated by a group of the people on the whole city and so on. Okay. Okay, Ali, what's your question?
What is the best way to solve this optimization problem? Do we have to draw the demand and supply function and find the intersection between them, or is there any more convenient way to solve this problem?
It's not. They will be the same. It's not necessary for you to draw the line. I mean, for this simple example, like for the example here, in this, I'm just for the example here, you have these two equations, right? And
yeah,
there are only two variables, p and x. You put these two equations together, you can easily get the answer, right?
Yeah.
So this p. So you put the first equation here. So p equal to 100 plus 0.005. X is 10,000 minus 50p. And you solve it, you get the result. So it's the same, you will get the same result. Or if you can solve the equation, that'll be the best. You can get the accurate result. And if we just go to check the figure, your result is approximate, right?
Yeah.
And similar to this one, only when it's really hard for you to solve the, like for this one, in the first example, well, we solve this one with the equation to find out the value of x1 and x2 prime. But if this equation, I mean, if this utility function is very complicated, I will recommend you to use this figure instead of solve it by hand or through the equation directly. So the it's quite flexible. You can either use the equations or use the figure to do it. I'm going to show you some. Actually, for the next big example, integrated example, it's the utility function is quite complicated, and it's almost impossible for you to solve it by hand. So that's the reason you need to get the figures and then solve it. So it's case by case.
Yeah, I get it. Thank you.
Any other questions?
Hi, Dr. Yang.
Yes.
I still have a question about utility. Can I think the utility just like the degree? I need this trip. How I need this trip, or how I satisfy with this trip.
It's something like because it's really hard to quantify the utility. Like if you go to a theme park, how are you going to quantify your utility? It's really hard. This might comes from some social science, and you need to. They may find out do some survey to quantify what's the actual cost, what's the actual benefit they can get from the utility from this trip. How they're going to enjoy playing in the theme park and so on. But for this kind of even for the transport system, we have some definitions. Like for this example, this is kind of the quite realistic utility functions. The only thing you need to think about is like the utility might be might follow some trend about the number of the activities. Especially when the number of the activities is too high, as it probably does not mean that the utilities can gain significantly. You just need to make sure that the utility function is insatiable, and is only related to the number of the activities and the type of the activities, not related to the price.
Okay.
So a lot of time, I will not ask you to define the utility or to find out the functions of utility by yourself. Usually we will, even for the government, for them to do some planning about the transport system, they will have some well-calibrated utility function for you to do the planning job. You don't need to do the calibration or collect data by yourself. Okay, I hope that answered your question. Anything else? Okay, if no, then I guess that will be all today. And also, like, just keep your mind about the deadline of the first homework assignment. And I will also post the second homework assignment maybe sometime later this week. But you will have another 2 weeks to work on the maybe 3 weeks to work on the second homework assignment. The example that I'm going to introduce next lecture will be highly related to your second homework assignment, which will be will cover most of the topics we covered. We have introduced in the lecture 2, 3, and 4. So well, hopefully can go back to go check the notes, the course notes, go through those definitions, and in the next lecture, once we go through the whole integrated example, you will have a better idea about how all these theories is applied for the transportation problems. Okay, if there's any questions, I guess that will be all about the lecture today. And I really appreciate your attendance about the class. Just feel free to send me email if you have any questions, and keep me posted, and or join the office hour. Okay, guess that's all. Thank you very much. Enjoy your week, and I'll see you next week.
Thank
Thanks
you.
very much.
Yeah. Thank you. Bye.
Bye.
Bye.